Hello? Yes?
Hello.
Okay, so we can start the fifth lecture by Tali. Now on neutrinos. Of course, neutrinos as dark matter. You heard quite some about sterile neutrinos, and he'll talk about some very exciting experiments to try to detect their signal.
Okay, so this is the last one. We made it. We're going to, at least some of us, because I can see that the herd is thinning down as the week goes by. All right, so today we're going to talk about detecting sterile neutrinos as dark matter. And I'm not going to give an overview of all the different ways. I'm just going to talk about mostly one particular way of looking for it, which is through X-ray observations of the sky. And I'll overview some of what has been done right now and some of the hints that exist for a potential signal. And then I'll talk specifically about a project that I'm the principal investigator on, which is the Micro-X rocket, and how we would like to use that platform to search for dark matter. Okay, so we've been talking a lot about dark matter, and there's a lot of discussion of what are the things a good model for dark matter should have. And we've had several people talk to you about the WIMP miracle and why that makes it such a compelling candidate for dark matter, because it comes out of supersymmetry. You have a completely separate thing that you're trying to solve, and it produces a particle that could be dark matter that has the right properties, right? The same thing happens for axions, as we were hearing yesterday, and we'll hear more today. Axions are a particle that's theorized for a separate reason to deal with CP violation, but it has the properties that you might want to, under certain circumstances, to be dark matter. So I think those are two very good candidates. A third very good candidate are sterile neutrinos, because if you look at our current knowledge of the standard model, we have our particles, and all of our particles that we know of have both right and left chirality. But the neutrinos that we have discovered so far are all left-handed. And so in the standard model right now, there are 3 boxes that are not filled. So there are 3 little boxes that there's no reason that they shouldn't exist, and that we have not found a particle to put in that box. Now, the other point is that we know that neutrinos have mass. And so that's outside of the standard model, and in order to give them mass, one of the best ways to do that is to put some particles in here that will interact through the seesaw mechanism to provide neutrinos with mass. So we have an anomaly that has been measured, that neutrinos have mass, that we know is physics beyond the standard model. We have 3 little boxes in our standard model that are unoccupied as of now. And so I think it's a pretty good motivation to say, well, hey, maybe one of those boxes could be the particle that we're searching for as dark matter, as a heavy sterile neutrino that would be cold enough to be dark matter. So this is not going to be the sterile neutrino that we've heard of that from the reactor anomalies or from mini-boon, because that's a 1 eV-ish neutrino, and that neutrino would be relativistic. It would be way too hot. That would be a hot dark matter candidate. It would not be able to fulfill the requirements that in order to have structure formation, dark matter has to be non-relativistic. And so this 1 eV sterile neutrino could be one of these boxes. So you could imagine in a scenario where there are several sterile neutrino species, one of them could be the one that is producing the anomalies, or it may not, we don't know yet. But another one could be dark matter, and another one could be one of the mechanisms to give sterile neutrinos mass. Normal neutrinos mass. So it's certainly a well-motivated candidate for dark matter. Now, if sterile neutrinos exist, and if they're dark matter, then sterile neutrinos can decay because they're going to oscillate, right? So they're going to oscillate just like normal neutrinos do. And there's a one-loop process where a sterile neutrino will turn into a standard neutrino and emit a photon. Now, of course, the standard neutrinos' mass are basically zero, right? They're very, very small. And so by momentum conservation, if this thing is heavy, then you're emitting two particles that are basically of zero mass. And so this photon is going to have an energy equal to half of the mass of the sterile neutrino. And so it's a line, it's a single energy photon that would be emitted with a mass equal to pretty much exactly half the mass of the dark matter particle. And so so that's a very compelling idea because now you have a decay process, whereas the dark matter can convert itself into a normal neutrino, and it's emitting this line that you can look for. Now you can calculate the decay rate of this particle, and it turns out to be something like this, where the main number here is 10 to the minus 29 per second, right? So the rate of decay is super, super slow, which is something that you need in order to be able to have the dark matter still be here, right? So this is not stable dark matter, but it is decaying so slowly that at this point it's mostly there. Now, the mass of the dark matter is around somewhere in the keV range. And so this is interesting because, of course, if you have keV mass dark matter, and when I say keV, it could be 100 keV. It's in that that range. Then you're going to be emitting photons that are on the 10s to 50 of keV, and that's a range where those are basically X-rays. So those are a range of photon energies that we have detectors that we can go look for them. So if you're going to look for dark matter, then you have to figure out, well, how many photons would there be, and would I be able to see them, right? So let's think about that for a second. So let's do some calculus. So if you imagine this being the dark matter halo, and of course it's a lot bigger, but it wouldn't fit in my screen if I try to put it all. So this is the galactic center, and here's the sun, and the sun is going around the galactic center. So there's a distance from the sun to the galactic center, and there is a dark matter density profile that goes as rho as a function of r, right? So that's like the NFW profile, or whichever profile dark matter actually has, but let's imagine it's the NFW profile for now. So you have some spherically symmetric density profile for dark matter. And so the flux of photons that I get from this guy is going to depend on the density here, and then I'm going to make some little volume element that's going to have some solid angle, so that's like a little circle, right, of a solid angle, and some distance dl, right? So I have a solid angle here, like a little circle there, and then some dl. And so the rate, the flux per little unit volume is going to be equal to the decay rate times over the mass of this plus this factor times the dark matter density. Now the dark matter density, of course, is a function of the radius from the galactic center, but we're not at the galactic center. So we need to convert that radius into distances that we are measuring, so we can convert r just through trigonometry into two variables that are L, which is the distance from us to that little volume, and the angle that that little volume is making between us and the galactic center. Does that make sense? So if I redefine r just through trigonometry into these variables, then I can just go ahead and integrate, and I can get the total flux through some solid angle going from us all the way out to the outside of the Milky Way to infinity. But of course the halo has some finite distance, so it's basically until you run out of dark matter. It's going to be something like this. So it's going to depend on your field of view, course, and it's going to go from 0 to infinity, and you integrate out your density. So you want to have as many dark matter particles as possible, right? So you're going to see the photon rate that you see is going to depend on how many dark matters you're looking at, and of course their decay rate. And so it makes sense that if you're looking for dark matter in the Milky Way, then this is not a great strategy, because you're only looking at this bunch of dark matter here, and look at all this other dark matter that you're not looking at. So if you're going to search for dark matter in the Milky Way, a much better strategy is to do that. Right? You want to integrate as many dark matter particles as you can. And so you want to have a really large field of view, so at any given time you're looking at, you know, a good fraction of all of the dark matter in the Milky Way, so that there's so many particles that even though the decay rate is super small, you are looking at so many particles that you have a chance of seeing the flux from those lines. Does that make sense? Now, when you look, if you're in the sun and you're looking this way, right, you could also look that way, right? You don't have to look at the galactic center, but if you look at the galactic center, then you have to figure out what the density is in here, which is an unknown right now. And so there's different debates on whether there are cores or not to dark matter in the Milky Way, and so or peaks or higher density. What does the density look at the center? And so, because you're integrating over the center, depending on the different dark matter profiles, that can make a big difference in the density at the center. So if you're looking at the galactic center, you can get a pretty big difference in the flux that you will see depending on what the dark matter density actually is, which is an unknown right now. So that introduces a systematic error into your measurement, or if you want to be optimistic, it gives you a way of actually measuring what the profile is if you're seeing a signal, right? Because then you can look at it and actually map out what that profile is. Okay, so just the same way that we do for WIMPs, we can look for these and parameterize these sterile neutrinos with some mass and some decay rate. And the decay rate is related to the mixing angle, so usually we plot it as a function of mixing angle. So you get a plot that looks something like this. So on the x-axis, again, we have mass. Now here we're in kV, so this is kV dark matter. And then on the y-axis, we have the mixing angle, which is very, very small, right? Sine squared 2 theta being a very small number. And so you can look to see if you see a flux, and people have done this. And so you can do that because this is X-rays. You can look at it with X-ray observatories like XMM and Chandra. And so that's these fits over here. This is Perseus, so you don't have to look at the Milky Way. If you have most of these observatories actually have a very small field of view, right? So if you have, if here's your dark matter halo, and you're here in the sun, and this is the galactic center, and your field of view is something like this, right? Then looking at the Milky Way might not be your best bet. But if you're looking at a cluster of a galaxy cluster over here that has a lot of dark matter, and it's really, really far away, so by the time you get there, you're actually imaging that whole thing, then the density here might be such that that's a better target. And that's the case for most observatories. So most observatories with mirrors that are imaging, like XMM or Chandra, will do better looking outside of the galaxy at other objects because they have a mirror. They could collect all the flux from some solid angle, and they want to look at a brighter source. So although the Milky Way is the brightest dark matter source in the sky, if you're only looking at a small fraction of it because you have a pencil beam field of view, then you don't win by looking at the Milky Way. So most of these limits are, for example, looking at Perseus, which is one of the brighter galaxy clusters, gives you one of the better limits. Looking at the Milky Way, you can still do pretty well, but it doesn't win at every point. And that depends on instrumental effects and other things. At higher energies, where you're getting up to 50 keV in the mass of the dark matter, these X-ray experiments are really made to work in the kind of 1 to 6 keV region. So when you get to those upper energies, you're using other experiments like NuSTAR or the Fermi GBM or integral. Right? So those are higher energies getting closer to gamma rays, so use other instruments. And then, yep. Yes, there are bounds. I don't think they're stronger. There are phase space bounds. So for example, if the dark matter is too light, then it won't allow structure formation. And so there's some lower bound, and that's around 2 to 3 keV. Okay. And there are other bounds for example, laboratory experiments and all that, but they're like way up there. They're in the 10 to the minus 6s, like over here. So the strictest bounds on this region come from these X-ray observations. Now, these are all instruments that have pretty wide pretty rough energy resolutions. They're like CCD type energy resolution, which is good for some things, but for this, when you're looking for a single line that has a width of somewhere between 3 eV and 30 eV, depending on what mass scale you're looking at on the object, then you really want a high resolution instrument. And you can't use a grating because this is a diffuse emission. So this is perfectly made for a non-dispersive spectrometer, which is exactly what a microcalorimeter is. So this is made for microcalorimeters. And this is a prediction of what the Athena X-ray telescope, which will have a microcalorimeter in it, would be able to do. And you can see that it can really go several orders of magnitude below the current limits. Now, I'm going to talk a lot about the 3.5 kV signal, or hint, and so this is kind of a plot that also has those potential signals there. But I want to stress that when you're looking for dark matter, we're not looking for the 3.5 kV signal. I mean, it's a possibility, and it's a hint, and we will look for it, but there's no reason that it has to be that, right? So it could be that dark matter's over here or over here, we just haven't found it yet. So it's, this spot right there is a perfectly good dark matter candidate. And so just because the 3.5 kV may or may not be a true signal doesn't mean that this entire region of parameter space for looking for dark matter is not hanging on that one particular candidate. Okay, so the question is there a bound from the cross section to get the dark matter abundance? Yes. So that depends on the dark matter, on the creation mechanism for the sterile neutrinos. So for example, if you just look at kind of the standard way that you would generate a sterile neutrino through just the universe being hot and generating all particles, you end up with this Woodrow window right here. So this is what you would predict if you just kind of took the vanilla cosmology and tried to generate the right dark matter density. And as you can see, that has been ruled out. But that doesn't mean that there aren't other ways of generating these sterile neutrinos. There's a lot of papers on this topic. There are many different mechanisms. One of the favorite is a resonance mechanism, where as the universe passes through certain temperatures, you can enhance the production, and it depends on some parameters, and you can basically tweak the parameters to get anything around here that will have the right density. But that's a good question. All right, so I'm going to talk for a little bit about the 3.5 kV line, because that's the kind of the more the thing that has gotten the most attention in the last 2 or 3 years. But again, I want to emphasize that this is a general dark matter search, not a search for this one line. But there's a hint, so we'll talk about it. So in 2014, there are 2 papers that noticed that when they looked at galaxy clusters and they tried to fit their data, they got what they called an excess in this region of 3.5 keV. Now, this is where you have to understand that there are particle physicists and there are astronomers, right? And to particle physicists, you look at this and you just say, wait, where's the excess? And you have to understand that this is in astronomy is a plus or minus 20% kind of stuff, right? Like you're doing. Now, this is a very complicated fit. There are a lot of the thing that is lost when you look at this graph is that the model that is being used to fit this data is very complicated, and it has a lot of information on it. You're using the temperature model for the plasma of the object. You're using the known atomic excitation lines for those temperatures. You're using the ratio of the species of metals that are known in the universe. There are a lot of parameters in these fits. And so it's actually pretty, and people have been working at this for a long, long time. So they're well understood models of how these objects should look like, and they're really well characterized instruments. And so people have been able to get very good fits of these curves. Now, there are tons of lines in this spectrum that you can't see because the instrument doesn't have the resolution to resolve them. So what you see as a hump here is actually a forest of lines. Okay? And so that's an important thing to note. But they have, they have done this enough that they do say, look, that is a significant excess. Now, it's not a 5 sigma excess, but it is an excess. So it's more the, 2 to 3 sigma region. And the same thing here, they have a little bit of extra flux, which when you look at the residual, you get some extra flux there. So after these 2 papers, Boyarsky looked at the Milky Way. Now this is again with the pencil beam, so what they're doing there is they're looking basically at something like this, where that's the bigger than the field of view, and they're looking at the galactic center. So they're doing a pencil beam through the galactic center, and they see, again, they see this excess, and they plot the flux that implies versus the predicted mass density. And they see that, then these lines are different time constants for dark matter. So this is the inverse of the decay rate. And they are roughly consistent. So, you look at the blank sky, you look at these 2 objects, and you look at the galactic center, and you see that the flux that you get will depend on the density. So the galactic center has a lot higher density where you're looking at it, and so this is all seems consistent. Now, a ton of people jumped on this and started analyzing data, and there were several papers saying, look, we look at this and we don't see any excess at all. And so then it became a long discussion of, are you modeling things correctly? And so are there systematic effects? And what are the predicted fluxes for all of these different lines that are inherent inside the spectrum? And then there were papers that said, no, you're using the wrong lines. Here are the revised fluxes for that same data, and if you do that, then you'll see the excess. And so there's a lot of atomic physics going on back and forth. People looked at other objects. They looked at galaxies, at groups, and at dwarf spheroidals. And they said, look, this is what we would expect to see, and we don't see it. And so there are a couple of papers that came around saying, oh, no, I don't see anything. And so kind of that was a dampening on the whole idea. people looked at the morphology of the 3.5 kV line and said, look, if we look at the 3.5 kV line in Perseus, this is what we see. Does it follow the dark matter profile or not? And there's the first paper said no, then there's another paper I'll show you that says yes. So there's a lot of debate going on. There were other clusters looked at and said, hey, look, I see this excess and it still is consistent with this general sort of decay rate or time constant for the dark matter. Then there was a deep observation of the dwarf spheroidal. And dwarf spheroidals are, you know, other galaxies that are in orbit around our galaxy, and they have very little stars. And so they're good targets because they're small enough that the field of view of these instruments can kind of see most of them. And there's very few stars, so there's a very small you know, background from all of the X-rays from the stars. So that's a good place to look for dark matter. It's a good signal-to-noise ratio object. And so there was a very long observation, 1.4 megaseconds with XMM, and there were two papers looking at the data, and these guys say, nope, I don't see anything. These guys say, I don't really see anything either, but if you actually look at the detectors, some of them actually see something and some don't. And so there was still some confusion, although I think it was definitely not as strong a signal or an excess as people were hoping for. They were thinking that that was going to be one of the kind of yes or no answers. People have looked at stack clusters, so this is 33, so you just stack a whole bunch of clusters together to get more signal, and you analyze them as one object. And they see a small excess, but again, this is really not enough to be able to claim anything. Then we went back to the dark matter profile and saying, let's look at the dark matter profile in Perseus. So again, you take your galaxy, if you have your galaxy cluster and you make lots of observations like this, and then you do fits, and you get some 3.5 kV excess in each of these, if you do, and then you plot it against what you would expect, and this is what they see. So this red dots are their data, and the black line is the expected flux from decaying dark matter following an NFW profile. And then this other points over here are the flux from atomic lines in the cluster. So you can see that those are definitely different. And so that's a paper saying, hey, look, we do see something that is consistent with what we would expect if this signal were dark matter. Yes, so Suzaku is a X-ray telescope that had a microcalorimeter from the group that I work with. But the microcalorimeter had a design flaw in the cryogenic system, and then it failed not too long after the launch. So Suzaku is taking data, but it only has the CCD cameras. There were several telescopes on that observatory. One of them was a microcalorimeter, and that microcalorimeter did not function. So then finally they said, well, let's, even though we have a pencil beam field of view, Chandra has looked at stuff for a really long time. So let's see if we can see the excess in the Milky Way outside of the galactic center, because the galactic center is really busy. There's tons of other stars there and low mass X-ray binaries, and the foreground is really rough when you're trying to subtract that to then get at the dark matter profile. So let's just look this way, where there's like nothing, basically. You're off the plane of the galaxy, through the dark matter halo, into a region of the sky that doesn't have any bright X-ray sources. These are these deep fields where originally were looked at to look for like really far redshift AGN and study high redshift object, so you don't want a bright X-ray source right in front of him, right? So you look at basically a blank piece of sky, and you look for 10 megaseconds, and then you start to look at all that X-ray background from galaxies and that kind of thing. So they did this analysis and basically found that in the Milky Way, their data, which is this diamond here, this is the axis that they saw. Obviously, it's a smaller axis, but compared to the Boyarsky observation at the center of the Milky Way, it's roughly consistent with what they would expect from the flux looking in this direction, given the dark matter profile. So again, this is still a debate. People are continuing to work on it, and it's not clear whether this is a signal or not. But it's definitely at least a hint, and people are continuing to work, and the debate is still going on. Of course, this is all you're seeing is an excess of a line. So that doesn't mean that it has to be sterile neutrinos. So a completely other set of work is a whole bunch of theorists saying, oh, hey, look, I have a dark matter model that will fit this line and will explain everything, right? So there's a lot of papers on different ideas for other types of dark matter, like exciting dark matter, so basically a dark matter particle that goes into an excited state and then decays, and that can be a much heavier particle, and what you're seeing is the energy difference between the two states, which would be 3.5 keV. Or there could be axions that are going through and emitting photons. You know, there's all sorts of other ideas of how you can make this. Now, I think the bottom line is that the reason that you have all of this debate is because you're using an instrument that is at its systematic. These are systematics limited observations. Two people analyzing the exact same data set come to opposite conclusions. And this is using mostly the same tools. They're just tweaking what the model parameters are. And so this is just, we are kind of pulling at the bottom of the barrel of what these instruments can do. Like, we're just systematics limited. So you really just need new technology to the rescue. And so, of course, we want to use microcalorimeters to search for this. So we need something that can see this line in the X-ray band. You know, that's what we need. So the successor to Suzaku, because the microcalorimeter in Suzaku failed, the Japanese and US effort rebuilt the satellite and launched a new satellite into space called Astro-H Hitomi. And unfortunately, this one had an even worse fate than Suzaku, because in this one the microcalorimeter worked, but there was a software glitch that had a -1 in their attitude control system. And so when the attitude control said, oh, I want to go this way to be stable, it actually fired the other way. And so it kept saying, oh, no, we need to, something is pushing us, we need to push harder to correct ourselves, and it would actually start to spin itself up. And it ended up basically breaking apart. And so this unfortunate software glitch made the entire telescope fail. Now, before it failed, it was doing some science, some of the first observations with this. So they actually did look at a cluster of galaxies. And this is a image of the instrument. The microcalorimeter is here, and there's this gate valve that's in here, and that gate valve had a beryllium window on it so that you could get X-rays through it, but the beryllium window didn't allow nearly as many X-rays as when the gate valve was open. And this was still in the commissioning phase, so the gate valve hadn't been open yet. So although they looked at the, these are the specs, the important one is that the energy resolution is around, was around 4 to 7 eV. So that would be plenty good to be able to detect the signal. So they looked at Perseus for 275 kiloseconds, but because the gate valve was closed, the effective exposure was more like 70 kiloseconds. And they analyzed the data. So here is the data. Now look at the energy scale here. Like, if you look at these previous you know, oops, no, that's not what I wanted to do. If you look at these lines, you know, this is going from 3 to 6 kV, right? Now when you look at this spectrum, this is going from 2.9 to 4, and you have a lot of points in there, right? So this is a microcalorimeter spectrum where now you can start to see all of these lines. And all of these guys here are expected lines. You can see these little tiny bumps. Those are all lines, like actual atomic lines you would be able to see. Now, just in the same way that there's some here that you can't really see, this observation was too short to be able to resolve all of the lines. You need to integrate longer to get better signal to noise. And so they don't see an excess in the 3.5 kV region, which is a pretty big blow to the whole idea, except that when you do the calculation, the flux that the limit that they see is actually not that strong because they didn't have as long observation as they would have wanted to. So if you take all that together, you can put sort of a status for the 3.5 kV line. This is a paper by Kev in one of my colleagues that has this really nice plot where he basically puts all of the kind of 2 sigma regions together and the limits. So you can see that, you know, these are limits from different analyses that don't see anything. Here's the Hitomi microcalorimeter limits, and you can see that although they didn't see anything, they can't rule out this center region. They just didn't have enough exposure to do it, which is super unfortunate, but you know, there we are. And so basically the point is that it's, you know, this is really in the 2 sigma, 3 sigma region, so you can't really say anything one way or the other. It could be an instrumental effect, although that has been studied and people have looked at different Z, you know, different objects at different redshifts, so the line would appear at different energies. So it's unlikely to be an instrumental effect, but you know, it's really a systematics limited measurement. Okay, so let's look at what we could do with a rocket. So sounding rockets have been around for a long time, and there's actually a microcalorimeter sounding rocket that has been around for a long time. So this is the XQC sounding rocket. It has flown 6 times. This is a photo from 1999. Here's me as a grad student going to my first rocket flight. And this guy has, we get about 300 seconds of on-target data for each flight, and it's a high-resolution X-ray microcalorimeter, which a large field of view. So this is kind of exactly what you want. Yes?
What is a sounding rocket?
So a sounding rocket is a rocket that, you know, if this is, let's see, if this is the Earth, I guess we can turn that cluster of galaxies into the Earth pretty easily. All right, there's the Earth. So this is the Earth. You know, an orbiting mission would launch, and then it would go into orbit around the Earth. Sounding rocket goes up and then comes back down. So it has a lot less energy. So you can use a smaller rocket, and it's called a sounding rocket because you're sounding the atmosphere at that region. You know, like this is it's a Navy term because this were Navy rockets. You know, like you sound the river to get its depth. So that's the sounding rocket. Is from sounding a river. It's a maritime term. So it's basically you are measuring the properties of the area above in the atmosphere. But it's a very parabolic path, so it really uses a lot less energy than if you're trying to get the, you know, you basically have 0 velocity at this point, whereas something in orbit, you know, has to be moving at 17,000 miles per hour or something like that, if I remember right. So that's what a sounding rocket is. And then you get it back, you have a parachute, you get it back. These launch from White Sands and from Australia. So this is the XQC Rocket Payload. So it's very, so it's a small refrigerator. This is called an adiabatic demagnetization refrigerator. The detectors are here. This is the refrigerant part that cools them down to 50 millikelvin. And this is what the array looks like. So it's a 6x6 array. And these are using silicon thermistors. So these is the kind of the original technology for microcalorimeters. They work great for this application, but you can't make super large arrays of them because each one needs its own electronics channel, and there's no way to multiplex the readout. And so you're limited to the number of pixels you can have. But this project has flown 6 times. So we collaborated with the PI of this rocket called Dan McCammon at the University of Wisconsin, and said, hey, let's look at your data and do a search for dark matter with it because it has all the properties that we would want. So we started by looking at one of the flights from XQC, which was flown in 2011, and this is a steradian field of view, but it was looking basically away from the galactic center. So the field of view of XQC, if this is the sun, was kind of like that, away from the galactic center. But if you calculate what the field of view of XQC looking away from the galactic center is, the ratio of the rate to the 14 arc minute view of XMM, which is like the pencil beam looking at the galactic center, is almost a factor of it's a factor of like 600 or something. So you get 600 times more flux than XMM did by looking at this big field of view because you're just integrating so much more dark matter, right? So even though you have a short flight, you actually get pretty close to the same, there's a combination of a lot more signal and a lot less background because you have a lot higher energy resolution. So each bin of that you're looking at has a lot less background. If you have 200 eV, your background is the sum of all the background that exists in that 200 eV region. If you now go to 2 eV, you have 100 times less background, right? So you get about a factor of 50 less background and a factor of hundreds more signal. So even though you have factors of, you have a lot of less observing time, you can actually do something that gets pretty close. Okay, so we analyzed this one data. We now have we're now working on analysis of all of the XQC data throughout its 6 flights, which is going to give us an increase of about a factor of 5 in our signal. So this is a view of the sky and in the X-ray from an instrument on the International Space Station. And this is the galactic plane. And this is SCO-X1, which is the brightest X-ray source in the sky. And this is the field of view that XQC looked at. Now, unfortunately, it had the crab, which is one of the other really bright sources in the sky, in its field of view. And it didn't care because XQC is looking at the really low energy X-ray background, and that's what they're studying, so they didn't mind to have the crab in their field of view. The other thing that was very unfortunate is that they need a calibration source to do their, to calibrate their instrument, and the calibration source happens to have a potassium fluorescence line in it that gives you a K alpha and a K beta line, and they lie right in between the 3.5 keV region. So not only do we have the crab, which is this red line here, we also have to deal with the fact that we have these calibration lines in. And then we get these bumps from photons hitting the substrate. I'll show you what that means in a second. But basically, this is the spectrum. And so we did a fit to that, and you can see the residuals here are pretty good. And so we can use that to make a limit on what, even though we have all of the signal in the region that we're looking at, you can still say, well, what is what limit can we put on how strong the coupling could be for us not to see an excess there. These 2 lines here are because the substrate that they used was a silicon substrate with this mercury telluride absorber on the top. Now, they were doing very low energy X-ray observations, so all of the X-rays would stop right there. But at 3 keV, some of them actually penetrate into the silicon, and in the silicon they give you a slightly different signal. There's more loss, so that's why you get these humps here are for our events that actually penetrated into the silicon. And so you have to take that into account in your modeling, but then you can turn that into a flux limit, so you can say, well, what's at 95% confidence the highest flux that we can rule out given the data that we have, and this is the result from that. And if you zoom into the 3.5 kV region, this is the claimed signal strength from Boyarsky, and this is sort of where we were at. So we weren't able to get enough, close enough to be able to rule it out or see it, but it's actually pretty amazing that with just one flight, we got that close. So by doing the analysis we're doing now of 5 rocket flights, we might be able to say something about it. Now, of course, we want to do this more, because the more we observe, the more signal we have. And so I'm the principal investigator of this Micro-X sounding rocket, which is originally a rocket to do X-ray astrophysics, to look at supernova remnants. But I'm going to talk today about the application of this rocket to this problem. So this rocket is actually a space telescope, so we actually have a mirror, and that gives us a field of view of about 12 arc minutes, which again is not very good if you're looking for dark matter, because that's again a pencil beam. So if we're looking for supernova remnants, this is great. But if I want to actually look for dark matter, what I want to do is I want to chuck out the telescope and then have a much larger field of view. Right, and that field of view is called grasp, which is your effective area times your angle, and you get a much better grasp without the mirror, which is what you want for looking at dark matter. Okay, so let's talk about just go through some pictures of what this looks like. So this is the design of the microcalorimeter for Micro-X. You have an absorber that's on these little posts, and then you have a TES here on the side. That's your thermometer, and then you have a weak link. This pinkish thing or salmon-looking thing is a silicon nitride membrane, which we use to decouple from the rest of the system. That's what the array looks like. So this is now a 12 by 12 array. So we have 128 working pixels. The size of this is pretty small, so we spend all of this effort to launch this tiny little chip into space. But you put this chip in the focal plane. You have these superconducting electronics that are going to read them out. These are squid chips that are multiplexing, so you only have 8 channels, but you're reading out 128 pixels. And so you take that and you put it in a box. You put that box in a superconducting shield, because the superconducting shield is needed to keep the superconductor from seeing the magnet the 4 Tesla magnet you're going to put underneath it to cool it down. You put that in this packaging. You can see the magnet right here. So this is the magnet, and here's the detector. So the superconducting shield is very important. It's 4 Tesla in the middle of this, and we need this to be at 0, field. And then you put that into a cryostat. All of this stuff that you're looking at, we designed from scratch. This is all designed in our group from scratch. None of these things is this. None of this is commercial except the screws. And so we made this, and it's basically spent about 10 years putting this thing together. It's been a really long road. And this is basically what the entire telescope looks like. And this is what goes inside of it. Okay, so you can do then the same calculation and say, well, if we look at the galactic center, which is a much higher flux, with Micro-X, you could actually get about 2,000 times the signal rate that XMM saw. So, you can imagine taking a view of the galactic center that looks something like that. And in order to predict what we would see, we have to model that. So we take a model that has the cosmic X-ray background that comes out from the extragalactic sources in blue. the galactic thermal model in the center that tells us what the galactic center looks like, then a model of the emission from the disk, and then you have to add, all of these black dots that are all these low mass X-ray binaries, so you have to add a model for all the low mass X-ray binaries. So make a census of all the known X-ray binaries and you add them up, and so you end with a model spectrum that looks like this. Now look at all these lines. This is the model of what you are actually seeing. And so this is what actually you're trying to resolve with these CCD cameras, where you're only looking at these, broad humps. So you can see that having higher energy resolution is really will give you a much stronger handle. So we have this model of what all the backgrounds are. We can then model what we would see in this 3.5 kV region, and you can see that the background is going to be pretty flat, not a lot of bumps. Then you can model what you would see in a rocket observation with and without the flux from the predicted dark matter signal. If you take the Boyarsky paper and say, okay, that they say this is their best fit flux, if you use that as a model, you would see that we would be definitely able to see that line if it were there, even in just one flight. This is about 300 seconds. It's very short. So you could also think about looking in other directions, because then you can start mapping the profile. So this is a really nice region here where there's very little stuff, right? So the background modeling is a lot easier. And it turns out that this is about a factor of 2 less dark matter flux. But because the background is lower, this is about the same sensitivity. So if you're really doing looking for the 3.5 kV line, this is actually a better field, because you get the same signal to noise and you get a much lower background. So if you see something, there's less questions about, oh, did you not model the low mass X-ray binaries right or something, right? So this is actually a much better field because the background is a lot easier to model. So there's less questions about whether you did that right or not. And we can also look, outside of the galactic center to compare the results with the XQC results, and again, kind of do that profile. So this is our projection for both the galactic center and the off the galactic center. They're about the same sensitivity. If you look at the XQC field, it's not going to quite be enough. So this is the prediction from Boyarsky. These are some of those X-ray constraints. And you can see that with one flight, we would definitely be able to see that line if it truly is from dark matter in both of these fields. Now you can also put this into this previous. This is a more updated plot with more limits. So this is kind of where micro-X would be. Now, especially if you look at that second field where there's very little background, you're basically doing a zero background. You expect less than 1 count per bin in that second field, because there's not a lot there. And so again, we have this discussion, if you don't have any background and you're doing exposure for dark matter, your sensitivity basically grows as MT. So this is a completely photon-starved measurement. So if we were to fly again and look at the second at that same field, the sensitivity would basically be double, because you're not seeing background yet. And so with 2 flights, we would get something that looks about that. So we would if this signal is there, we would definitely be able to see it. Now you would say, well, but why would you want to do that if Athena is gonna have so much more sensitivity? Oh yeah, that's true, but Athena is going to fly in 2028. And that's what they say now, and it's probably going to be 2030, or who knows, right? So that's still at least 10 years away, and we can do this now, right? So there's I think this is a really interesting case where there isn't another mission that has this type of sensitivity for at least a decade, and this rocket has this unique capability to make this measurement. Now, another thing that you could do if you actually saw this signal, which is super cool, is that this is a line, right? It's a very sharp line. The thermal measurement is about 3 eV. So you could actually think about the fact of, well, wait a minute, the galaxy is rotating, and there's this WIMP wind. So could we actually do directional detection with this signal because of the Doppler shift? And the answer is you can. So this is a paper by, not by us, by a group at Stanford that basically modeled the micro-X response and said, hey, if you look at different angles, the Doppler shift is enough that you can see it, and you could actually fit the movement of the galaxy through the dark matter. And that would be a telltale signal that you're seeing something that is not on the galactic disk, that is not co-rotating with you. And so that would be a very strong evidence combined with a profile that what you're looking at is really dark matter. Okay, so I'm almost out of time, so I'm just going to finish by just showing you some fun pictures, because 2 weeks ago we were in New Mexico, and this is what we were doing. So this is the Micro-X payload. This is me, this is my son, and my wife, and all of the team that was there putting this rocket together. Here's the microcalorimeter. You can kind of see that little red thing there. That's a microcalorimeter in there. And this is the optics. And these are all the electronics. And then this is the two-stage rocket boost, solid rocket booster. And so on the night of July 22nd, we were working for 7 weeks straight trying to get this thing put together. It was 7 weeks of not sleeping, and so it was pretty exhausting. But on the night of July 22nd at midnight, we actually launched this thing. So let me see if I can. Where's the microphone? Let's see. Does this one work? All right. Let's see if this works. Oh. All right, we'll do this one on too. All right, let's see if you guys can hear this. I have to go over here. No. That took a lot longer. So different views. All right. So that was the launch, which was very exciting. Although, of course, we didn't see it because we were in the control room. So my wife got to see it and I didn't. So let me see if I can find my. Okay, so we launched this thing at midnight, and then the next morning at 6:30 a.m. We go on a helicopter and go find this thing out in the desert. It was about 50 miles from where we launched it. So again, it's a very parabolic flight. And you know, it's out in the middle of nowhere, except that there are these, if you look at this picture, you can see these big holes. And if you look around, you'll see a couple of them. They're like these big, we think there's another one right here. There's like badger holes. So we're hoping none of these badgers would come out because they're like, holes like this big. Like that's whatever digged that is pretty big. And there's another one there. You know, there's a whole bunch of them around. So we were kind of a little nervous about that, but we didn't see any of the badgers. And so then we went down and got the rocket. When it landed pretty hard. So if you can see, there's like a little seam there that's broken. The bolts actually broke, and it basically broke into two pieces. So this joint there failed. But this is actually great because this is the joint between the NASA part and the telescope part, and our part actually looks pretty intact. So we take that and we put it on the helicopter, and you know it doesn't fit, so you have to fly with the doors open, so that's pretty awesome. You're going like 120 miles an hour, about 200 feet off the ground, because these are Army helicopter pilots, so they fly at full speed, really close to the ground, with the doors open. So it was really awesome. Yeah. We had. Let me see if you can't see them here. We have these cradles that we put around, and it's kind of like it's like a half circle, and then there are bars on the side, and then like 6 people will grab it and just kind of. So yeah, you got to huff it out. There's no other. And so we got the telescope back. I don't have any results to show you yet because that happened 2 weeks ago, so I haven't even looked at the data yet. I'm still recuperating from the effort, but we will be definitely working on that. We can tell you that the detectors worked. We saw X-rays from our calibration source during the flight. So at least from a technology point of view, it was a success, and we're hoping that we'll get to fly this sometime soon. So I want to conclude all of the classes so far by saying that this is a really exciting time for dark matter. We have lots of different places where people are looking, where there's an interesting possibility of finding dark matter in the next 10 years. So, for you guys, this is a great time to get into this field. I think that WIMPs are really interesting, but people are starting to look at other places. So you have a really wide variety of experiments and the size of the collaborations and the techniques used to work on. So as an experimentalist, if you wanted to get into this field, there's lots of things to choose from. There's people looking at axions with squids. There's all these, CCD. There's like all the liquid noble stuff, the bubble chambers, microcalorimeters. I mean, there's so many different technologies out there. So there's something for everyone in terms of what type of experimental work do you want to do, and this is a great it's a really nice science, important and exciting science theme to work on. So I think I'm going to stop here and say that we're looking. We don't know where it is yet, but if we're lucky in the next 10 years, somebody will see something, and then it'll basically change the face of physics and of what we do after that. So thank you so much.
Great. So let's take a couple of questions.
Actually, 3 seconds question.
3?
Yeah, but it's the same thing. Almost the same. Why do you need in situ calibration? How can you manage the banging your detector all around?
Right, well, that's exactly why we need the in situ calibration. You have a detector in a refrigerator, and you're basically hitting your refrigerator with a hammer for 40 seconds, and you're expecting your detector to stay cold and to have a perfectly flat baseline. And so we actually do accomplish that, but there's still some heat that is flowing around in those 300 seconds, and so we have a calibration source so we can do drift correction, gain correction as a function of time.
And you show a line, an escape line that is exactly on this signal. Why we cannot explain that 2 sigma signal with the actually manganese escape line?
Because it's a potassium, and so we know what the it's not exactly on 3.5 keV, and we know that there are people that are saying that the 3.5 keV line could be an atomic excitation from potassium. That is one of the that's one of the debates that's going on. It basically depends on what the abundance of potassium is in the galaxy. And you measure the amount of potassium in the sun, and then you measure the temperature, and that gives you a flux from these lines. And this is part of this debate, is that these are really hard things to do. If it is potassium, we will be able to see it with micro-X. We'll be able to pinpoint that energy. If we see a line, and we see it at a known atomic line for potassium, then that would be it. And then we say, okay, well, it's an atomic line, and that's that. So that's part of one of the results that could come from this observation. It'll also depend on the distribution of the potassium, even if it's not potassium. Let's just say it's some weird atomic line we don't know about. Because we're looking at a really large field of view, any one source is not going to be enough for us to see a signal, whereas XMM is looking at a really small field of view. So if there's a population of objects in the galactic center that are emitting more potassium or emitting some other line that we don't know about, XMM would see it. When we look at our big field of view, we wouldn't. So if we don't see anything, that's another indication that it really is an atomic line from a population of sources that's in the galactic center, is not spread out all over the place.
Okay, since he asked 3 questions, we are running a little bit late. So I ask you, as always, write down your questions.
Do you want the?
And you have the opportunity to ask them to Tali later.
Okay.
Great. We do see some cables. I presume is Andrews. Yeah?
Interesting.
So you know, he vanished from the Earth for 7 weeks because of the experiment. And we know that because we were trying to contact him to confirm if he was coming, and he was nothing. So we were really afraid he was not being able to make it to the school. But then our contact said, no, look, he's at NASA. He's like crazy. He doesn't even breathe. Well, I guess he was breathing, but maybe not eating too much.
Definitely not looking at my.
Yeah, but we're very lucky that the launch was before the school and we could have him here.
It worked out.
Dates worked out perfectly.